This video contains some comments on the PowerPoint that goes along with section 1.1. There is a difference between valid and true arguments, and I've copied a passage here from a textbook called Introduction to Logic. A deductive argument is valid when its premises, if true, do provide conclusive grounds for the truth of its conclusion. So the important thing to notice here is that we're sort of assuming, we're thinking about the situation where the premises are true, even though they may not actually be true. So you can have a valid argument that has false premises, but we have to think about if they were true, would the conclusion also be true? And then here's a different statement of something similar to that from the textbook. Right? And a different way of saying it, at least two statements are treated as facts, even though they may or may not actually be true facts. So here's an example of a deductive argument, and this is a valid form. This is called the law of detachment. So not all deductive arguments look like this, but this is a common one. So this is the setup. You would have two different premises. You have one that says if P then Q, and then the second one is P, and therefore we conclude that Q must be true. So here's an example. Let's say the statement is, if it is 2 o'clock, I am in class. All right, and then let's say that the next statement is, it is 2 o'clock. All right, so first of all, if you look at the true or false value for these statements, so for the first one, if it's 2 o'clock, I am in class, that may or may not be true, depends on the person. And then it is 2 o'clock, depending on what time you're watching this video, that may also be false as well. So we're not really concerned with true or false. We just need to know if we accept these statements as true. So imagine or suppose that if it is 2 o'clock, then you are in class. Then that means that if it is indeed 2 o'clock, then it must be true. It follows from that. There's no getting around it. That means, therefore, I am in class. Okay, so in this case, P is the statement, it is 2 o'clock. Q is, I am in class. And then we know P, it is 2 o'clock. So therefore, Q, I am in class. Now there's an easy way to make that valid argument into an invalid one, and that's by starting with Q as the second premise instead of P. So let's see what this would look like. Let's do a true argument first. All right, so this one's valid and true. So let's say if it is a living dog, then it is breathing. Okay, so that's if P, this is P, then Q. All right, and then next if we assume P, it is a living dog, or let's make this specific. Let's call him Spot. So Spot is a living dog. Okay, so that's P again. Then the valid conclusion would be, then Spot is breathing. We can conclude Q. Spot is breathing. All right, now this one on the right, this is an invalid argument, and this is called the fallacy of the converse. Fallacy of the converse. And a converse statement is just when you switch the hypothesis and the conclusion. So in this argument, we've switched the places of P and Q at the end. All right, so the argument would look like this. If it is a living dog, then it is breathing. Spot is breathing. And then the conclusion would be Spot is a living dog. Okay, so that's invalid reasoning, and since this one is does start with true premises, what we're assuming Spot's breathing, then this is easy to think of some counterexamples to show why the reasoning doesn't really make sense. If Spot is breathing, there are lots of different other animals he doesn't have to be a living dog. Alright, and then one other thing that I didn't think was very clear from the textbook, when you're trying to identify the hypothesis and the conclusion of a statement, it is helpful to write it in if-then form. So here are some examples. The statement, all carrots are orange, and any statement that's like this, that's like an all or an every, followed by a property or what it is, those can all be translated over to if-then statements. So for example, the all carrots are orange could be translated, if it is a carrot, then it is orange. And every dog has 4 legs could be written, if it is a dog, then it has 4 legs. And then all quadrilaterals are squares could be written, if it is a quadrilateral, then it is a square. Okay? And this is a visual way to represent if-then statements with a Venn diagram, and I think it makes a little more sense to think of this if you refer back to this all or this every form. All right, so if P then Q, this is like saying all P are Q. All right, so let's go with the carrots statement, and even though this one's false, there are other colors for carrots than orange, but we'll assume it's true for now. Okay, so we're saying that carrots are P, carrots, and then Q, this is the set of all orange things. So we're saying all carrots are also orange, so they would fall inside that category of orange things. That's why the circle's smaller and inside. We're not saying that everything orange is a carrot, so that's why the orange circle is larger to allow for that. Okay, and that's it. Just a few comments on section 1.1.